Welcome to the another session in Frontiers in CFD. So today we'll see the CFD simulation of thermal vent of lithium-ion battery using PCM and Baffles. So these are the objectives. Create a precise 3D model of the cylindrical lithium-ion battery with Baffles for realistic PCM-based thermal analysis. To set up the mesh PCM properties and do the setup and applying the boundary conditions in the fluent. Lastly, to run the simulation and generate the temperature contours and steam lines in ANSYS. So this is the geometry that we are going to follow. Only the change which we had with respect to the previous one is uh, instead of using air as a working fluid, the surrounding to the cells and surrounding to your casing, a PCM material has been placed. So how the PCM will affect the total temperature of system as well as the cell temperatures of the system, so that we are going to visualize today. Welcome you all to another session on Frontiers in CFD. Last time we have prepared the CFD simulation for airflow arrangement with Baffles. Today we are going to use the same geometry and we'll check out how the system will perform when we are considering the PCM as a material along with the same baffle plates which we are having. So let's open the geometry which we have prepared earlier. With the same geometry we are going to do the analysis on the system, and accordingly we'll see how the PCM will affect the performance as well as how effectively the cooling will be done, whether it is air cooling will be more effective, whether the PCM cooling will be better in this situation. So let's first open the geometry part. So let's click on edit geometry in the design modeler. So the same geometry will appear here as which we have seen previously, only we have to do some minor modifications in the geometry. So this is your fluid, this is your fins and casing, and this is your cells. So now this is, instead of this fluid, now we will rename this as your PCM. So carefully remember, we are specifying this as a PCM, and accordingly we will proceed for the simulation. So fins and casing, this is PCM, and these are your cells. So this is now specified as a solid, and now we'll proceed with the next part. So rest of the things we are not going to change. Only thing we'll just go on to add the fluid flow fluent option. Click on mesh, click on edit. So we'll use the same element size what we have used previously for the simulation again. Okay, so if the geometry is not loaded, close the meshing part, and one more time open the meshing to see if the geometry is properly loaded in the meshing section. So now click on fit to zoom. So you can see in the mesh, so just put the element size as 11001. And let's make it generate. So we are trying to use the same element size which we have used earlier, and accordingly we are going to proceed. So we want to compare the results, so that's why whether the system with air cooling will be more effective or whether the system with PCM cooling is more effective, that we want to visualize, and that's why we are trying to take same number of nodes and element what we have taken in the previous example. So So the meshing may take some time depending on the system configuration. So you can see the statistics as what we have seen previously. It is the same as the one which we have seen previously. Okay, so let's do one thing. We'll uh, just give the name selection and other thing with the parameter which we require. So first go to the geometry. Now in this case we don't need inlet and outlet. I will just go to the cell. I will say hide all other bodies, and I will now select all the portions. So this will be my cell boundary. So this is my cell boundary. Now let's make it show all bodies. So first section which we are defined as a cell boundary. Apart from that, if you want, you can actually define the PCM boundaries as well. So if I just show PCM and hide all other bodies, so this will be your PCM. So if you want, you can select it, otherwise you can keep it as it is over here. So this is for your PCM boundary. For selection point of view, it may be useful later on. So if you are selecting that, that is also one of the good option to go for. So but you need to select all the parameters which are been available, and then you can make as the PCM boundary as well. So this might be useful for us in the later stages if we are defining it. So let's go and select define this. So create name selection I done. Then I has put this as PCM boundary. So I specified cell boundary, I specified PCM boundary, and let's make it show all bodies. So let's make it update, and you will see the mesh translation to fluent successful message will appear as here. So once this task is done, we'll save the geometry file as well as we'll save the setup file, and then we'll proceed for the next step. So let's click on here, save the project. So you can select the desired location where you want to save. So I just put it with a different folder. So I'll specify 9 cell with casing and PCM cooling. So I specified 9 cell with KCM and PCM cooling. So I can put the same name here. I can specify as 9 cell with casing and PCM cooling. So let's click on save button, and now this work will be saved. So you can now close the geometry part as well as you can close the meshing part as well. So now next step is proceeding toward the setup. So while proceeding toward the setup, we must have some of the following parameters, like which PCM material you are using. We are using so you must know the properties of that. What is the density of liquid, what is the density of solid, what is the specific heat of liquid, thermal conductivity of liquid, viscosity, then pure solid melting heat, solidus liquidus temperature. So these all parameters are required when you are proceeding for the next step, that is for your setup. So let's close this meshing part as of now. So this is not required further. You may close the geometry part as well. So let's close the geometry here. Now go to the setup part, click on edit. So depending on the number of processes your computer can run, I will just put it around 16. Let's put it on double precision. Let's click on start. Specify the gravity, specify the transit model, and then we will proceed. So first we have to wait till the time the object is loaded, and then we can proceed for the next step. Now you can see the object is completely loaded, so you can just click on transient model, select the gravity, so put it to minus 9.81 here, then go to the models, click on energy equation on, then you have to turn on the viscous. I will put it here K epsilon, then enhance wall treatment, thermal effect, curvature correction, and let's click on OK. Then I will also click the solidification melting on. Last time when we are tried with air cooling, we have not done that. So this is the first. Now next is your material. So create edit. Instead of now air, we are going to use the PCM as a material. So you can define the PCM which we are going to use. So here I will put it as paraffin wax, first of all liquid. So here also you have to specify the paraffin wax liquid. So specify the density of the paraffin wax liquid. So I will just put it 790. Specific heat 2150. Thermal conductivity 0.22. Viscosity 0.01. Pure solid melting heat 240800. Then solidus temperature 313.6. Liquidus temperature 317.7. So let's click on OK here. Now we have defined the paraffin wax liquid. There is no other liquid which has been present. So I just go and edit, specify D here. Okay, so let's make it change grade. Okay, so name I will keep it as it is. So let's check if it is possible again. Okay, so not an issue. Next is we have to define the PCM material. So I will specify this is as PCM solid here also. So carefully write down what you have specified. So PCM solid. Then specify the density of PCM solid. Let us say 880. Then specific heat I put it 2000 here, and let's this make it as a 0.2. So this is your define for PCM solid. Okay, now PCM solid is also defined. I need the aluminum as also material. So first of all I just click on aluminum. So click on copy, then close. So for aluminum I just go and specify this again as the lithium battery. So I just put it lithium battery here. For second also I will put lithium battery. So you will use the properties like 2775. Then this is your 880, and this is your 3, that is watt per meter Kelvin. So let's make it change grade. So this will be your lithium battery. So now the third metal which I want to add is your solid, that is aluminum. So make it copy and then make it close. So we have three different materials as of now. One is paraffin wax liquid, second is aluminum, then lithium battery, and then the PCM. So next is defining the cell zone condition. So specify the zone type. Cell I want not as a fluid, I want it as solid. So make it solid here. So the cells will be made up of lithium battery. So define the source term. So I will just go with the value which we have shared earlier. So let's go with 104017, that is watt per meter cube, that is heat generation per unit volume. So let's make it apply and then close. So here fins and casing also I will turn it to solid, and then no need to define the source term over here. So let's click on apply and then click on close. So PCM I just go inside and will visualize if the PCM wax liquid is by default the name is available or not. So let's make it apply and then close. Go to the boundary conditions. Now in boundary conditions, you are observing it as a zone type. So we'll see cell boundary contact region TRG. Let's go inside and visualize if the material which are defined are properly or not. So here I will specify lithium battery here. Earlier it was showing the PCM as a material. So for each and every case I have to go there and select the respective material. So go inside of this. So here instead of PCM solid I will put it lithium battery, make it apply and then close. So this you have to check it properly. So for all the cells you have to do this. Go inside, define the material, that is lithium battery, make it apply and then close. So same way you have to do it for all the 9 regions which are available with us. So make it lithium battery, make it apply and then close. So make it apply and then close. So whatever meshing we have done, and after that we have done the mesh selection over there. So name selection which we have done earlier, so this is helpful now because we are easily able to identify which material belongs to which. So here you can by default observe cell boundary contact region. So you can come to know this is a cell and we are specifying the respective material for the same. So let's make it apply and then close. So at 7 also I will just go to the edit, then click on piece lithium battery. So make it apply here, make it close, make it apply, make it close. Then 8, go to the edit. Now in edit I will just put it lithium battery. So make it apply, then close, make it apply, then close. Here also I will just put it edit. So I'll just put it lithium battery, make it apply here as a apply and then this is close. So this is cell boundary contact region we are having. So PCM boundary contact region, you just check if the material is showing PCM or not by default. So yeah, you can see the PCM material has been available, so no need to look for the other things. So walls, pins and casing, so select the appropriate material. So wall pins and casing is made up of aluminum, so make it apply and then click on close. Similarly wall cell, you have to select the appropriate material. For wall cell it should be your lithium battery, so carefully select lithium battery, make it apply and then you have to close it. So we have done it for all the respective things. Now we'll go to the report definition. So I will recommend it to use the report definition later. First you can go with the uh, solution animation, then you can go back here. So first of all I will select temperature, I will select total temperature. So I will select the total temperature of system. So that's why I'm first going with this. So I will put it system temperature report definition 0. So let's make it OK. Now close this. I will just go to the solution in initialization. In initialize I will click on initialize. Once it is initialized you will see the patch option available, and then we'll go to the solution animation and we'll try to visualize how which is the zone corresponds to cell, which is the zone corresponds to PCM and other. So this will be easy for us to again define the material in report definition. So once this is available, so I just go here. So go to the solution animation. Now first of all I just click on the contours. So select temperature, here select the total temperature, select all, go to the color map option. Instead of exponential, click it on float, make it apply, then close, save display. So now the object will be loaded. So let's click on close, select the contour 1. You may specify uh, total temp, or I will specify system temperature animation. So let's make it OK. So second one which we will do is go to the new contours, total temperature. I will now just select all cell boundary contact regions here. So carefully observe, I am selecting only cell regions, and let's go to the color map option, make it float, make it apply, then close, click on save display. you will be able to see only cells. If they are not visible, there is something wrong with you. Okay, so this is one thing carefully you have to do. So second, which we have done, is the cell temperature. So I will put it cell temperature animation. Okay, so third one, most important, is the solidification melting. So I'll just select solidification melting. Now you cannot select all the regions, you have to select the specific regions only, then only the things will be correct. So I just first select the PCM boundary contact region. So let's make it apply, then close. So first I have selected only PCM contact region to ensure that whatever uh, we are done is correct or not. Okay, so wall PCM boundary I will select. So this is also the portion which we have selected. So make it save display and select contour 3 as liquid fraction animation. So let's make it okay. Okay, now go to the report definition. So I just go with now cell temperatures. So surface report, area weighted average. I will select temperature. So I will select total temperature. Now I will select only cell boundary contact regions here. And the last one, I will say cell temperature and go. So this is what the name I have observed here. So let's make it okay. And then one more thing, surface report, area weighted average. You will see solidification melting, liquid fraction. Now I will select PCM boundary contact region, make it PCM boundary, let's say here, and specify the liquid fraction. Okay, so liquid fraction curve I will specify, and let's make it okay. Now we are done with the report definition as well. So go to the run calculation, and so let's put it fix for a while and just put it 1, or let's put it 10, and then we'll visualize the things. So let's click on calculate. So what should be the thing initial stage? In the initial stage, we should not observe any kind of liquid fraction present. So gradually, when the heat is been dissipated from the cell to the casing, and from the casing to the PCM which is surrounding, so after that we will should be in position to visualize the liquid fraction. Till the time it doesn't reach to that solidification melting point, we will definitely not see any kind of liquid fraction which is present. So after the first 20 iterations are been performed, you will see the various windows which are been visible here. So let's wait for the first 20 iterations, and then we'll check out how the windows will show the different parameters as what we have set specified in report definition, as well as what we have specified in the solution animation. So 5 to 6 iterations are left. Once that is completed, you will see all the windows which are appearing. So now you will see one by one the windows are appearing. So this is the cell temperature which we can see right now. Sorry, this is total temperature system. This is, you will see the cell temperatures as of now. This is the contours of liquid fraction. The liquid fraction curve right now, it is completely flat, representing 0. It means there is no liquid present as of now. So till the time we don't reach the solidification melting point, you will not be able to see the liquid which is been present. So this is your cell temperature that shows your rising curve, and this is your the system temperature, that is again the rising curve. So we definitely have to wait for some time in order to visualize the simulation. So once the temperature reaches to somewhere around, as per the solidification melting point, that is 313 to 317.6, so we'll be able to visualize the liquidification and melting. So we are around 280 time steps. You can see how the total system temperature. This will show you the cell temperature. This is your PCM liquid fraction. We don't observe any liquid fraction as of now because temperature is around 307. So we'll see the liquid curve is flat. So this is the cell temperature curve. This is the total temperature system curve. So we have to run this further in order to visualize how the fluid will, how the PCM will be subjected to the liquid fraction, and whether any drop in the temperatures for cell temperature as well as for system temperature. So that we'll be able to visualize once we run it for further till it reaches to the solidification melting point. Okay, the work has been saved. Now we can run it further. So the simulation is completed for around 1200 seconds. So this represents the total system temperature. This represents the cell temperature curve. Next one, you can observe the liquid fraction curve. Then this is the contours of liquid fraction at 1201 seconds. Then this is the total temperature system. So based upon this, we have generated the results with PCM. So last time we have seen the results with without PCM, that is with airflow. So today we'll compare the values. So you can see the chart. First one, the values which were taken previously was the cell temperature with airflow. So you can see the temperature range is quite higher on the higher side, which is more than around 340. whereas if you say the second one, that is cell temperature with PCM. So here we can observe the temperature ranges are around uh, just slightly above 314 Kelvin. This is how the things are differ when we are comparing the two values, one with the air as a working fluid which has been present. Second one, we are considering a cell temperature with PCM, where we are not having air present, but we are used the paraffin wax as a liquid. So you can see how the temperature curve getting flat before the temperature which we have seen previously. So here we can see the cell temperature curve, which is with airflow. It is slightly on the higher temperature side, whereas the cell temperature curve with PCM, that is on slightly on the lower side. So if you want to save the simulation file, go to the workbench window, click on save button. So if you want to access the file later on, you can use this particular option. Just like we have done it for cell temperature, we can the same way we can do it for the total temperature of system as well. So this is the graph which is already been available with us. You just need to add one more graph which is for your cell temperature. So we'll just see how the cell temperature will which we can visualize over here. So for this you have to go to the cell temperature system temperature curve. So go to the notepad file, click on copy all the data which is been visible till 1200 as a flow time. So you will see how the system temperature varies with respect to the flow time in this particular case. So just click on copy. Once you click on copy, go to the Excel file. So put the data wherever it has been required, preferably especially on the side which we are already having some values. So let's put it. So make it use text import wizard. Click on next, and lastly click on finish. So the one which we don't require, just try to trim it. So these are the two things which we don't require. So this is the total temperature of system. This is with air as a working fluid. So first column represents the total temperature of system with air. The second column which represents the total temperature of system with PCM. So one of the case which we are considered earlier was air. The second case which we are considering is with the PCM. So now simply go to the chart and just update the chart and get the values for the total temperature of system. So you will be in position to visualize how the total temperature of system varies with respect to the flow time. So simply click the values, check out the values, extend these values in the other column. You will get the total temperature of system as well. So let's expand it on the other side. Go to the charts which we have generated. So this is a chart which we have generated. Now you can go to the Excel levels. So here you can see the total temperature which is visible. So you can set the location of this. So legends we want at bottom. So you can see the total temperature of system with air. Second one, total temperature of system with PCM. So you can visualize the PCM with PCM, the total temperature of system is limited to around 31, slightly above 316 Kelvin. So this is how the variations which we have visualized in terms of the combinations which we have seen previously. Okay, so this is the graph which we have generated. So simply use copy this graph and put it somewhere here. So let's take it on the other side. So this represents the total temperature of system with respect to the flow time. how the variations are there with respect to temperature, that which we can visualize over here. So this represents the contours of total temperature of the system. How the total temperature varies with respect to the flow time is visualized here in this case. Previously we have considered the case with air as a working fluid. Now this is the case with PCM as a working fluid. So PCM as a fluid, as a material which has been present. So the solidification to melting as takes place once it reaches to uh, the the temperature which we have specified during the solidification and melting as a material definition in the properties. So right now it is for 600 flow time, we are observing the temperature is around 315.93, so it reaches to around 316. So till around 800 time steps we are observing it is around 317. For 1000 time step it is around 317, 318, and for 1200 seconds you will see again it will be around in the range of 3189, 318.89. So this is the variation. So this represents the liquid fraction. As of now we are not able to see any kind of liquid fraction which is visible. So till the time we don't reach to the solidification and melting point, we'll not be able to visualize any other color contour which has been specified over here. So right now all these things represents blue, so that indicates the liquid fraction is not at all present at the initial stages. So till the time we reach to the solidification and melting temperature, you will see some liquid fraction that will be visible in the animation video. So for a 500 time step we are not observing anything. So now we are around 600 time steps. So now you can see the liquid fraction has been visible. So that means it has reached to the solidification melting point, and the melting of the PCM has been taken place. So for around 800 the flow time, the liquid fraction is around 0.37. For around 900 seconds we observe it is 0.53, and for around 1000 seconds we are observing it is 0.60. So till the time we reach to around 1200 second, so this value may go beyond 0.7. So you can see the last value, that is 1200 second. So liquid fraction which is visible is 0.75. So this represents the cell temperature, how the cell temperature varies with respect to flow time. So that is now visible. So as the cells are surrounded by casing and the casing is surrounded by PCM, so the PCM will take heat as far as soon as possible till the time when it reaches to the solidification and melting point. So you will see 309.50 as of now for a flow time of around 400 seconds. So till around 1200 seconds, this value of temperature may slightly change. So we are now to that point where the melting is likely to take place. So in the properties we have specified around 313 to around 317 Kelvin. So for 800 seconds it is approximately around 317 Kelvin. For 1000 around it is showing 318. So it might not go more than 318 as per the initial guess. So we are approximately to 1200 seconds, and it shows the value of temperature as 318.89. So this represents the cell temperature with respect to flow time. You will see the curve will get slightly become flatter after around 600 flow time. So this represents the liquid fraction which has been visible for around 1200 seconds. So this represents the total temperature of system, how the total temperature of system varies with respect to flow time, that we can visualize here. So this is a comparison point of view, how uh, the cell temperature varies if we are using the PCM as a material for absorbing the heat, and second one if we are using the air flow through that particular channel which are surrounded by the fins as well as the casing. So you can see a considerable drop in the values of temperature, which is approximately around 315 Kelvin. So that represents the cell temperatures are maintained at comparatively lower temperature if we are going with the PCM as a material. Whereas if I just go with air as a working fluid, definitely this is not the better option to go for, because the temperatures are almost reaching around 340 Kelvin. So this represents the total temperature of the system with PCM and without PCM. You can clearly see how the system temperature is affected by using the PCM, and second one if it is being used with air, we can see comparatively higher temperature on the other side.